In this video, we'll use Chai-1 on Neurosnap to model a protein with residue modifications, specifically a phosphotyrosine-containing peptide in complex with GRB2. SH2 domains generally recognize phosphorylated tyrosine residues and play a key role in cellular signaling. So in this example, we're going to show how a single post-translational modification can directly drive binding and molecular recognition. So specifically, we're going to be using Chai-1. It's a great protein folding model and has a similar architecture to the AlphaFold 3 model. Additionally, what we're going to be using is this protein over here from UniProt. So what we'll do is we're just going to remember the UniProt ID over here, and then we're going to head over to our input sequences. We'll enter the ID, and Neurosnap will automatically fetch the sequence, the amino acid sequence, for that protein. Now for the peptide sequence, we're going to use this peptide over here, and to add a post-translational modification or residue modification, we're going to click here, and then we're going to set it to PTR. So what exactly even is PTR? Well, if we head over to our CCD database, which we can access over here, we'll quickly let it load. If we want to look for PTR, we can see that it corresponds to O-phosphotyrosine. So when we specify a post-translational modification or residue modification using any of the AlphaFold 3-like models or some of the other tools available on our platform, we're usually going to reference that modification specifically using its CCD code. So the CCD database that we offer is just a quick way to kind of visualize and search for things, as some of the other databases are not as easy to navigate. Alternatively, we can also type in something like phosphotyrosine, and boom, we have all different phosphotyrosine options available within the CCD database. Now, if we go back to the actual Chai-1 submission, we can see that we have a couple other options. For this particular example, I'm not going to mess around with applying restraints or anything like that. And then for settings, we have a couple different options. For MSA mode, we have single sequence or using MMSeq2 to generate an MSA. Chai-1 is particularly cool because we don't actually have to generate an MSA like some of these other tools. They also use the ESM2 language model to generate embeddings, and after those embeddings are used to kind of supplement using an MSA. So this is a little bit less accurate than an MSA, but it's a lot faster and it's a lot less resource intensive, and the accuracy is also extremely similar. And in some cases, actually, for de novo proteins, single sequence mode has been observed to do a little bit better. So for this one, we're just going to stick to single sequence. Now, recycles is also another one. If you ever use AlphaFold 2 or Boltz 1 or any of these other models, the number of recycles basically corresponds to a longer amount of prediction time as the number increases, but also a greater amount of accuracy in most cases. So basically what recycling is the model will take its prediction and kind of refine it and run it through the model a little bit more. In general, 6 is sufficient, but in some cases, if your accuracy is a little bit lower, you can increase this to 10 or 15 or a higher number, which has been observed to drastically improve accuracy. The fusion steps and the fusion samples are not particularly important in this particular case. This is a number item you can use to kind of increase the model's internal sampling steps, which can increase accuracy as well in some cases. And the fusion samples just corresponds to the number of output structures. In our case, 5 output structures is sufficient. So what we'll do is we're going to hit run job, and we're just going to let this run on Neurosnap's cloud environment. And then when it's done, we'll be back with the results. We are now back with the results, and as we can see, this job took hardly any time at all, only 57 seconds. And right off the bat, the structure does appear to be quite accurate, as we can see from the blue regions. These blue regions, by the way, are PLDDT scores, and they basically indicate the model's per residue confidence in a particular residue's orientation in space, as well as its rotation and whatnot. So overall, the PLDDT does look quite good, and the peptide itself, we can see it over here. It seems to be binding in the right region, as if I remember correctly, the region it should be targeting is roughly 60 to 160, which is the SH2 domain. And what we can do actually is we can highlight that a little bit better. So 60 is more or less around here, and 160 is, oops, let me redo that. Letters are a bit small. Right over here. Actually, that's a little bit too much. We can remove some of those, and we can remove some of these. But yeah, it seems to be targeting the right region more or less. Now, if we head over to different scores and we look at the scores table over here, we have a couple different metrics. So over here, the quality, the overall quality does say very low, but I wouldn't worry about that too much just because Chai-1 outputs overly pessimistic aggregate scores. So in a lot of cases, Chai-1 will produce an aggregate score that predicts the structure to be a lot lower quality than it actually is. But generally, mean PLDT as well as IPTM, if you're using something to predict interactions, that's a little bit of a better indicator. Additionally, min IPSAE is really good as well for this. Additionally, we can shift between models over here. So for instance, if I wanted to switch to model 2 as we outputted 5 different models from this run, we can do so, and we can also change chains over here, and we can see that the PTR residue is right over here. Now, as we can see overall, the PLDT is strong for this particular set of predictions, but the PTM score is fine, like 0.6 is definitely within a tolerable range. However, the IPTM score is not very high, so it's more likely, or at the very least, Chai-1 personally doesn't think that this is a very likely interaction, which is unfortunate, but that's just how you'd interpret these scores. Generally for IPTM, you want them to be, at least 0.7 or somewhere within that range. We have a couple of presentations on this as well. Additionally, we have the PLDTs over different residues over here, so you can see that right here. We offer the per chain IPTM. So this is the IPTM scores between each of the different chains. It's basically an output matrix. And then we also have the PAE matrix. So if you've seen our AlphaFold 2 video or some of our other structure prediction videos, this is interpreted in basically the same way. And then finally, we also have PDE. So if you've seen our AlphaFold 3 video, I believe we discussed PDE a bit as well. And then finally, we offer a couple different metrics related to the interface. So this is IPTM, just calculated in a slightly different way using a different library. And additionally, we have IPSAE. So this is the main metric that we like to use to discriminate between metrics. Surprisingly, the IPSAE is actually quite high. So maybe this is a real metric. In these such cases where you have conflicting results, the best thing to do sometimes is also to repredict the structure using another model like Boltz 2 or Protonix or something else, and just seeing how consistent that is. And you can also just take the result and throw it into like a GROMACS molecular dynamics simulation. These are all tools and models that we offer on the Neurosnap platform. So definitely an interesting observation. I wasn't expecting to see a high min IPSAE score. And then we also have different ways that the min IPSAE scores were calculated and normalized. So this is the one for domain scale, and then we also have the residue scale one, which is a little bit lower. But long story, and we also have LIS. So LIS is another good indicator. If you watch our last workshop related to protein binary design, which we'll include in the description, definitely a good resource for learning when to use these metrics and how to evaluate them. So that's essentially everything. Additionally, what I'll do is I'll show that you can see the configuration over here as well as the inputs over here within this tab. You can see the files that were uploaded as well as any of the files that were produced, and you're more than welcome to download them. And then finally, we have the citations as well as the option to create a share link. So for instance, if you create a share link, you can now send this to someone else and they'll be able to access the job. But that pretty much wraps up our tutorial. If you learned something or have any questions, please feel free to leave a comment and we'll try to get back to you. Additionally, if you want to make suggestions for future videos, please leave a comment as well and we'll be more than happy to try and tackle that topic. Anyways, take care and enjoy the rest of your day.